Basic machine learning relies on linear classifiers. These algorithms separate different categories of data by drawing a simple, straight boundary line through the dataset. That works when your data is neatly clustered, but the real world is rarely that organized. When confronted with complex, nonlinear structures, standard linear models fail to categorize the information accurately. These two scatterplots show data patterns a single line cannot resolve. Left, concentric circles. Right, the XOR problem. Forcing a straight line through these curved or disjointed shapes causes inaccurate predictions, as the model mathematically cannot bend to match the geometry. Because simple linear models cannot comprehend these complex structures, we have to find a new mathematical perspective to separate them. Curious, the theoretical solution is to take the data in its current state and map it into a higher dimensional feature space. This diagram shows the mapping effect. Inseparable 1D points are lifted onto a 2D parabola, where a straight line easily separates the blue squares and gray circles. A linear predictor in this new, higher space effectively becomes a nonlinear predictor in the original space. Introducing the complication. However, real-world problems require more than a jump to 2 dimensions. To capture complex patterns, we might map data into thousands or even infinite dimensions. As this slide outlines, calculating massive feature vectors explicitly causes the curse of dimensionality. Mapping a 100-feature input to a 5th-degree polynomial grows the dimensions exponentially. The required memory and processing power is so high that explicit computation becomes impossible. We are caught in a paradox. The theoretical solution works, but implementing it directly would break the machines we use to run the math. To move forward, we need a mathematical workaround, a way to utilize those higher dimensions without actually performing the massive calculations required to go there. This workaround is made possible by a principle called the representer theorem. This mathematical presentation of the representer theorem details a specific constraint. No matter how vast the high-dimensional space becomes, the optimal solution isn't in some unreachable corner. Instead, it lives entirely within the span of the data, expressed as a combination of original training examples. Because the final answer is tethered strictly to our existing data points, we can find the result without ever having to construct the entire higher dimensional space. These equations demonstrate the resulting loophole. The algorithm only needs to calculate inner products, the mathematical relationships between feature vectors, rather than the vectors themselves. We satisfy this using a kernel function, a direct replacement for the impossible step of mapping points to higher dimensions. This table contrasts the hard way with the smart way. On the left, manually constructing high-dimensional vectors becomes exponentially expensive. On the right, the kernel trick calculates that high-dimensional inner product directly from our original low-dimensional space, bypassing massive intermediate calculations entirely. The kernel trick mathematically simulates the predictive power of higher dimensional spaces without requiring the computer to pay the computational price to go there. Not every function is a valid kernel. It must satisfy Mercer's theorem by being positive semi-definite, ensuring a true inner product. By building a gram matrix with this kernel, we mathematically guarantee we implicitly perform a linear operation in a higher dimension. This principle expands the scope of existing algorithms. Any machine learning method expressed purely in terms of inner products can be kernelized. This side-by-side comparison shows the conversion of standard ridge regression. By substituting the kernel function into the objective, a rigid linear algorithm is transformed into a powerful nonlinear tool without ever catching the high-dimensional vectors. This flowchart summarizes the entire conceptual journey, moving from the limits of linearity through the obstacle of dimensionality, and finally to the efficient solution provided by the representer theorem and the kernel function. The kernel trick is a masterpiece. It upgrades simple models into complex pattern recognizers through the elegance of mathematics.